So I'll turn my video off. Okay, so I'm Vincent from the University of Mines and Technology, Ghana. And on behalf of my co-authors, I will present our work on towards efficient discovery of target high utility item sets. This is the presentation outline from the concepts to the conclusions and future works. So I understand that most of us are already familiar with the concept of high utility item sets or utility driven data mining. So when we talk about the high utility item set mining, it's just a task that is used to reveal items that are of high importance when we are looking at quantitative um, databases. So if we go to the quantitative customer transactions, for example, high utility item set mining will reveal items which, when bought together by customers, yield the highest profit. So just a brief overview of some concepts in high utility item set mining. The first one is what they refer to as the quantitative transactions or database. And by that, it simply implies that the items in the database, we are looking at the items and the quantities that occur in the database. So if you look at transaction one, for example, it simply implied that the customer bought 4 units of D, 2 units of E, 1 unit of F, with 7 being the total number of items bought. And let us keep in mind that when I'm referring to internal utilities, I'm simply referring to the quantities of the items in the database. The next we need to take note of is the external utility database, and this simply depicts the importance that is attached to the items in the quantitative database. So for example, A with 3 simply mean that when we sell a unit of A, the profit return is 3, and a unit of F will give us a profit of 9. So the next we need to look at is the utility of an item in a transaction, and basically expressed in equation 1. This is just a product of the internal utility and the external utility with that item. So if we look at the example, item D in transaction 1, it has an internal utility of 4 and an external utility of 3. So the product of that gives us the utility of item D in transaction 1. So given the utility of an item, we can compute the utility of the item set in a transaction and express in equation 2. It is just the sum of the utilities of all items that are in the transaction. I think someone is on mute. So when we look at the example like A and B in transaction 3, the utility of the item set AB in transaction 3 will be evaluated as the utility of A in transaction 3 plus the utility of B in transaction 3. And that gives us 3 by 1 plus 2 by 1, and that gives us 5 as the utility of the item set AB in the transaction. So given we can evaluate the utility of an item set in a transaction, we can likewise calculate the total utility of the item set in the database. And expressed in equation 3, it is just the summation of the utilities of that item in all transactions that it appears. So for example, if we look at the item set AB in the quantitative database, AB occurs in transaction 8 and 3. So its total utility will be the utility of AB in transaction 3 plus the utility of AB in transaction 8, and that evaluates to 13. So with the concepts to high utility item set mining, we can now define a high utility item set as any item set whose total utility is not less than a user specified minimum threshold. If the utility is less than, then that item set is a low utility item set. So why the concept of target high utility item set mining? With the traditional high utility item set mining, there are some challenges. So for example, when we use a traditional high utility item set mining, they end up reporting a set of high utilities that are either too large or too small for decision making. If the set is too large, some of the reported high utility item sets may not be useful, or it makes it difficult to decide which ones should be used for decision making. If the set is too small, it could be that some of the useful high utility item sets may not be reported. And finally, they end up ignoring the targets or interests of users. So the user is interested in a set of items that are of high utility, but it reports more without taking note of what the user wants. So either the user have to search through to find those that he or she is interested in, or you keep adjusting the utility threshold until those that are of interest are reported. So I will simply use this example to explain or show the challenges with the traditional high utility item set mining techniques. We assume that the user is interested in high utility item sets that contain either E and or F. If we set a minimum utility threshold to 10, traditional high utility item set mining techniques will report 36 high utility item sets. The burden is now on the user to search through these reported ones to identify those that contain E and or F. So this is not the first work on target high utility item set mining. There are some initial solutions which use either post-processing or pattern matching, but they also have some known challenges. And these are, firstly, to use these techniques, you have to scan the database twice. In the first case, the database is scanned to obtain information about the unique items in the database and to compute their transaction-weighted utilities. In the second scan, all transactions are compared with the user target before they are now sorted using the computed transaction-weighted utilities. So in essence, what happens is whether the item co-occur with what the user is interested in, its transaction-weighted utility will still be computed. And all transactions, including those that do not co-occur with the user target, will still be compared and scanned twice. So again, I'm using this to illustrate the challenges that are in the existing techniques. So we have our user target as E and F with a minimum utility of 10. So all transactions that are highlighted red, they will be scanned twice, even though they do not contain the user target E and or F. So again, if we want to use the post-processing techniques, all the 36 high utility item sets which were shown previously will have to be discovered. Then a search through the 36 will now report the 12 targeted high utility item sets which contain E and or F. Another challenge is that they will compute again the transaction weighted utilities of all items, including those items which never co-occur with the user targets. So for example, the items A, C, and G, they never co-occur with the user targets in the entire database, but their transaction weighted utilities and their remaining utilities will still be computed during the discovery process. So our proposition is aimed at presenting a target high utility items miner, and we are looking at scanning the database once. With the help of the user targets, we drastically reduce the search space for the target high utility items mining. So our approach in essence will end up reporting the set of high utility item sets based on the user targets, and it will not create the utility list. It will not compute the transaction weighted utilities of all items, and it will not compute the remaining utilities of all items as well. So I will use this example to explain how our implementation works, but for detailed explanation, please refer to the paper. So in our implementation, the first step to mining the target high utility item set is to find a set of length 1 item sets and their respective transaction IDs and the internal utilities. So given the database, our approach it looks for the single items in the database and return their cover sets as well as the internal utilities. So if you look at the A, for example, A occurs in transaction 3, 5, 7, 8, and 9. So its cover sets or transaction IDs will be stored in a data structure, and the corresponding internal utilities will also be stored in a different data structure. Given that we have identified the unique items and their details from the database, what we need to do is to find a set of transaction IDs in which we should search for the target high utility item sets. So initially, we are using the intersection of the transaction IDs of what the user is interested in. So E and F, we find the intersection, and that gives us 1, 4, and 6. These are the transactions which contain the user targets, and these are the only ones we should search for the user targeted high utility item sets. So given the transaction IDs which we are interested in, we now do a pruning of the items and their respective information with regards to the transaction IDs and the internal utilities. So this is the data structures before and after pruning based on the user targets. Once we have been able to prune the search space, we will be able to obtain the set of items which co-occur with the user target. And in this case, we have them as BD as the set of items which co-occur with the user targets. So we use the set of items together with the user targets to extract their external utilities from the external utility database. And we store that in another data structure. So as we can see, in the data structure for the utility database, we don't have A, C, and G because they do not co-occur with the user targets. So with the external utilities obtained, we now find the set of length 1 target high utility item sets. And here we are using only the user target because the user is not interested in B alone or D alone, but high utility item sets that contain either E or F. So we use the internal utilities with the external utility data structure to compute the total utilities of E and F only, and that will be the length 1 target high utility item set. So given the length 1 has been found, we now look within the pruned search space, and our approach will repeatedly mine the set of target high utility item sets from the pruned search space with their cover sets and the corresponding internal utilities. So it will use a modified version of the a priori to generate the candidates without scanning the database again. We will be able to get the support from the cover sets of each of these length 1 items. So in the long run, we will end up reporting the 12 high utility item sets based on the user targets. So for our experimental analysis to check the efficiency of our proposition, we use these data sets with their properties. We obtained the data sets with the internal utilities, so we had to synthetically generate the external utilities of these data sets. So we compared our proposition with D2HUP. We could not readily obtain the implementations of the post-processing and pattern matching, but D2HUP is the fastest, one of the fastest high utility item set mining algorithms. And it should be noted that D2HUP will be more efficient than all the post-processing techniques and slightly less efficient compared to the pattern matching techniques. Our experiments were conducted with regards to runtime, reported target high utility item sets, as well as the memory usage. So we use different targets as can be shown on the slides. So for our proposition, we had different targets to see how it performs compared to the D2HUP. And we had the minimum utility thresholds. We observed that in both figure 1 and 2, when you increase the minimum utility threshold, all algorithms will run, use the shortest time to run. But when we decrease the threshold, then they use a longer time to discover the high utility item sets. So, but what is to be noted is that our techniques or our technique is relatively more efficient compared to the D2HUP, which will be more efficient compared to the post-processing and slightly less efficient to the pattern matching. So we again did the comparison in the chess data set and it can be seen that whilst ours is running around 0 point something seconds, D2HUP is taking about 4,900 seconds. In the COSARAC data set for the runtime, we had exceptions with the D2HUP, so it is only indicating our approach with the respective targets. We just did, this table is simply showing the reported high utility item sets, what we obtain if we use the target of the user versus what will be returned, and among which the user will now have to search for the high utility item sets that contain the targets of the user. So T1 and T2, they are the same targets for the legends in figure 1, 2, and 3. And we can observe that the targets that we have, our technique will always return a smaller set of high utility item sets from which the user can now make decisions based on the reported item sets. So the last analysis was on the memory usage, and we can observe that for the food math, figure 6 and 5, they are the same, just that figure 6 excludes the D2HUP, the memory usage of that. That is because the memory usage of our tool, based on the targets, they are relatively very small, so we need to expand that for the visualization of the reader. So when we look at it, our technique was it is using about roughly 4.65 megabytes maximum. D2HUP is using about 3,000 megabytes of memory. However, it should be noted that our implementation is in Python currently, and D2HUP is in Java. In the mushroom data set, again, we can notice that our proposition, irrespective of the target, is running around 30 megabytes maximum, whilst the D2HUP is running minimum about 2,200 megabytes. So in conclusion, we have presented a target high utility item set miner, and is able to use a single database scan with the help of the user target, drastically reduce the search space and return the high utility item sets that actually contain the user targets. For our future works, we are looking at how we will be able to improve our proposition using the pseudo projection. We are also looking at a way that we will be able to further reduce the search space reduction in the first scan. How we can implement the approach using the FP growth, not the original FP growth, but a modified version, because we don't want to scan the entire database in the second scan, and implementing other variations of our proposition to meet the desire of users. So at the moment, if the user is interested in target high utility items that contain a set of items, should it be only those that contain all those items, or one of them, or a fraction of the user target items? Thank you for your audience.
Yes, thank you for the presentation. Any questions? Yeah, it's a very interesting topic. So I got one question.
Okay.
How do you set up the target items? I mean, what is the kind of a target item that you are interested in?
Okay, for our experiment, in the experiment that we did, so presently we pick the top frequent items and mix it with an infrequent item. So we set a minimum support threshold. We look at the top frequent items, then we pick some of them are top the frequent items, and we look at those that are not frequent. So if you see the targets, for example, some they are different. So one of the shorter one is mostly all frequent items. Then we mix it with some that are infrequent.
Yeah, so it's understandable that you pick up some top, for example, top K items. Yeah, let's say frequent item set. But how do you choose the infrequent item set?
How do we choose the frequent items?
Infrequent ones.
Oh, we looked at the database. So we have a minimum support threshold. So for example, in the first case, we set a minimum threshold to 50%. Then we get the top K frequent items. We reduce the minimum support to maybe 40%. We get those that are frequent. Then we go to the least frequent ones among the 40%.
Yes, but why they are called the target items? Any specific criteria for those items that they need to pick up?
For example, that is what the target item is, what the user wants. So if we look at the example, we have about 36 reported if we mine all the high utility item sets based on the minimum support, the minimum threshold of 10 utility threshold. But the user only wants item sets that are of high utility that contain E, or item sets that are of high utility that contain F, or item sets that are of high utility that contain E and F. So it is the decision of the user. The user is not interested in high utility items that contain A and D. So how do we get that for the user? So it's the discretion of the user in selecting which ones he or she wants as the target.
All right. Yes. Thank you. Any questions? Yes. Hey, you want to say something? All right. Thank you for the presentation. Let's move to the next one. So, Philip, would you like to say something?